Hello, today we are going to present the work Effect of oleic acid weight fractions on hBN-based nanofluids, developed at POLO research laboratories, emerging technologies in cooling and thermophysics, working with electric materials laboratory from Federal University of Santa Catarina, Brazil. Miniaturization of electronic components led to increasing heat dissipating rates, demanding an improvement in heat transfer capacity. Working fluids with good thermal and dielectric properties are desirable in order to help attaining proper thermal management while electrically shielding the components. However, in some of the more demanding applications, relying solely on the basic fluid properties does not guarantee that the design requirements are fulfilled. Some studies assess the enhancement of thermal and electrical characteristics of commonly used dielectric fluids through dispersion of nanoparticles. Despite the promising results reported in literature, dispersion stability remains an issue, since it deteriorates over time and depletes the heat transfer capability and dielectric strength of suspension. A more stable working fluid can lower the cost of maintenance and improve the cooling system's reliability. By dispersing hBN nanoparticles, it's possible to enhance electrical insulation properties on the base fluid, given its outstanding dielectric strength, while improving thermal properties that will certainly boost the heat transfer performance of the working fluid. The addition of nanoparticles may improve thermal properties, but in some cases it is necessary a large weight fraction for significant results, and the larger the weight fractions, the greater are the chances of having a quicker deposition. To be commercially viable, nanofluids need to maintain stability over time as long as possible. It was observed a considerable improvement of thermal conductivity while maintaining dielectric strength in the desirable range. Thermal conductivity was substantially enhanced at a synthetic dielectric oil sample by dispersing a 2% in mass of hBN nanoparticles, obtaining a nanooil with a small increase in density and viscosity. It is known that nanofluids can be stabilized in many ways, and one of the state-of-the-art methods for stabilization is the addition of surfactants to diminish particles interaction and therefore prevent agglomeration and settling. The stability of vegetable oil-based nanofluids containing magnetite nanoparticles using oleic acid as surfactant was improved. Through spectrum and thermogravimetric analysis, it was shown that nanofluids with oleic acid were the most stable after 12 hours of dispersion. In the present study, the optimal weight fraction of oleic acid in hexagonal boron nitride based nanooil is investigated in order to obtain maximum dispersion stability and efficiency for analyzed fractions. For the solid phase, weight fractions vary from 0.1% to 5% were considered, and for the surfactant fractions of 5% up to 20% were evaluated. Dispersion stability was assessed through UV-Vis, spectrophotometry, and qualitative analysis over time. A critical aspect of the dispersion process is the need for a precise temperature control of the samples, which was ensured by using an ultra-thermostatic bath to maintain the sample contained in the copper beaker at 5 Celsius degrees. It is noticeable that the sample with 70.5 of oleic acid showed the highest absorbance levels when compared with the other fractions. After 6 days, This behavior is owed to the addition of oleic acid that promotes an increase in the nanofluid's capability of dispersing nanoparticles until it reaches a dispersion saturation point. From this point on, a considerable decrease in absorbance is observed, believed to be related to a complete depletion of the base fluid's dissolution properties due to an excess of dispersant. The maximum stability is observed with 17.5 in weight fraction of oleic acid. There is a subtle increase in the sample absorbance from 5% until 17.5% of oleic acid for the sample of 1.5 weight mass fraction of hBN. From this point on, the absorbance decreases, suggesting the existence of an optimal weight fraction of the dispersing agent for this specific hBN concentration. There are 2 points of maximum stability in the last time frame, 10 and 12.5%. There are similarities between measurements taken in the different periods. For the absorbance value obtained right after dispersion, a pattern of ascending value is depicted, beginning with 5% up until a peak value of 12.5% and decreasing after that. Weight is also presented for the 6 days time frame, however, with 2 optimal points at 10% of oleic acid. By looking at data for the 5% of hBN concentration, it is clear that there is no dispersion of nanoparticles at all after 6 days. This behavior possibly occurred because an hBN saturation point was attained, so the oleic acid concentrations considered in this study were not sufficient to obtain a stable and homogeneous sample. 6 days after the dispersion of nanoparticles in the base fluid, the samples which would better portray the performance of addition of oleic acid and nanofluids were put side by side. As expected, the nanofluids with fewer hBN particles, 0.1% in the case, presented no deposition patterns, so the considered oleic acid quantities were more than sufficient to ensure efficient dispersion and stability. On the other hand, the samples containing 2% presented superior stability over 6 days of dispersion, a remarkable result for this hBN weight fraction. The absorbance results depicted optimal value of dispersion concentration for all samples considered, with the absorbance value increasing up until this inflection point and plummeting after it. In addition, with the contribution of the dispersing agent, it was possible to disperse rate fractions greater than those proved to be impossible to attain with minimal stability in previous studies. An optimal point for oleic acid fractions was determined to tested samples. Besides the fact that the samples were stable for hBN weight fractions up until 2% after a 6 days period is an outstanding result. Furthermore, the thermal and electric properties of enhanced hBN nanooil samples with oleic acid have to be measured in order to determine if the presence of the dispersing agent has any influence over these key parameters. Such estimates is paramount to establish such nanofluid as reliable and efficient option regarding electronics cooling. Future works may as well benefit from using hBN nanoparticles with smaller particle sizes. ONS and previous studies This has shown to be relevant parameter to dispersion effectiveness. Those are the references. And thanks for listening. And don't forget to comment if you have any appointment or questions. Have a good day.